Hello, I'm Angelos Pagonas, PhD candidate at the University of Pavia and member of the GECKO Doctoral Network. My research is focused on immersed isogeometric analysis and mass lumping for structural dynamics. Starting from the boundary-fitted approach, we present the spectrum comparison between isogeometric analysis, or IGA as we call it, and standard finite element method. As we can see by plotting the discrete eigenfrequencies normalized to the exact solution for the whole spectrum, IGA has superior spectral accuracy due to its higher order inter-element continuity compared to standard finite elements limited to C0 continuity. That makes IGA competitive for dynamics. In addition, increasing the polynomial degree P helps IGA converge to the exact solution, while standard finite elements fail to approximate the higher modes. To introduce the immersed or trimmed approach, we present a brief overview of the finite cell method. But in general, the main idea is similar for all methods employing immersion or trimming. And the idea is to embed the physical domain in an extended domain that is much easier to discretize with a regular grid. This approach is ideal for complex geometries, and the meshing and remeshing process can be simplified a lot. But the presence of almost void elements with a small physical contribution can be problematic, as we will see in the next slide. To investigate the effects of immersion, we choose a simple bar setup. In the left plot, we can see the IGA basis functions that discretize the bar. The variable zeta is the moving immersed boundary implemented symmetrically from both sides and can replicate many immersed or cut element positions. The red lines indicate the element boundaries. By increasing progressively the immersion boundary towards the element boundary, the physical volume decreases until the two boundaries coincide, meaning a whole element is completely outside of the physical domain, and keep increasing zeta will repeat that process. On the right plot, the maximum discrete eigenfrequency is presented for several polynomial degrees. As the immersion is increasing within an element, the maximum eigenfrequency diverges to infinity. When the immersion is exact to the element boundary, here, the values are similar to the boundary fitted case, and the same repeating pattern can be observed. The behavior on the right plot corresponds to standard finite elements with either consistent or lumped mass matrix, and for the IGA implementation in the case of the consistent mass only. We will review the IGA lumped mass case in the next slide. It is important to keep in mind that in explicit dynamics, the critical time step is inversely proportional to the largest eigenfrequency. As a result, in the case of a diverging largest eigenfrequency due to the presence of tiny cut elements, the critical time step can become impractical and lead to infeasible simulation times. Now, moving to immersed IGA with lumped mass matrix, due to the high continuity of the basis functions, the largest eigenfrequency does not diverge. It is interesting also that this happens regardless of the trimming scenario and can provide larger time steps, allowing for faster simulation times. This is a great benefit for the explicit methods. But then there is the question about the impact of IGA with lumped mass on accuracy, and this is an interesting topic to explore. So to investigate this, we can create an example in explicit dynamics employing the central difference method and see the effects of consistent and lumped mass in both IGA and standard finite elements. But before proceeding with the problem setup, let's have a look at the time step based on the immersion that is going to be used for this problem. We present it in the same configuration as the largest eigenfrequencies earlier for several immersion cases. The benefit on the time step already discussed can be now presented clearly, as we can see on the right plot. Immersed IGA and mass lumping, these blue and orange lines, can provide a larger time step that is almost the same for any immersed scenario. The problem we set up to investigate accuracy is a traveling wave, and we can measure the global displacement L2 error between the numerical and exact solution. It is interesting to highlight the large difference between the consistent and lumped IGA errors, as we can see with the blue and orange lines. As a result, we can conclude that isogeometric analysis with row-sum mass lumping can provide larger, stable time steps. But that important benefit comes with a significant cost in accuracy. Based on that, the research goals are to further investigate and understand the effects of mass lumping and immersion, to extend the studies to fourth-order partial differential equations, and also to the 2D domain, and hopefully investigate better approaches to mass lumping for isogeometric analysis. Finally, I would like to thank you for your attention.